Hello, I'm Maximilian Engel from FU Berlin, and I will talk about optimization-driven dynamics with stochastic noise and gains, which is a collaboration with Georgios Piliouras from Singapore University of Technology and Design, whom I actually met at a similar kind of conference 1.5 years ago, roughly 1.5 years ago at Imperial College London, also thanks to Boumediene, whom I would also like to thank for this opportunity to present some of our research here. And this has been a very interesting collaboration, as I said, which was started in this context of machine learning and dynamical systems. And as the title already reveals, it will be about stochastic aspects in game theory, which hopefully will be of high interest also for people who are more into the real machine learning or artificial intelligence research, and I hope that these mathematical results can also help there. So the AI context for us, why we think that this research we have been doing really is important for AI and machine learning research, is the following. So there are AI programs who learn to improve themselves in different tasks by actually competing against other players, either human players or other AI programs. A very popular example is the generative adversarial network, which has been discussed quite a lot in the last years, which, for example, comes into play if you have a generator which generates certain images, which then compete with actually real images, and a discriminator network decides if the images shown are fake or real, and the AI tries to win each round by generating images which come closer to the real images, and the whole process is driven by some random noise. And this is not exactly the noise we have in mind for our study, but still that's already where the idea of a distribution or probability distribution around choices of an AI really play a role. And the crucial point, though, is really that this is a setup where we can model the whole problem as a game which is played, and where at each step the machine tries to improve itself in a task in order to win rounds in this game. This can be applied not only to images, but also to generating other products like music or videos, and is definitely a very important motivation for game theory in machine learning. A similar example to this one, also in the context of game theory and machine learning, is the very famous and highly celebrated question behind game design for or like designing game machines which are then able to win in highly complicated games against highly sophisticated real players or other AIs, as has been seen with the work by DeepMind in terms of AlphaGo and AlphaZero. And this kind of game optimization in AI programs, of course, has also been seen in chess, in StarCraft, and other examples. So there is a huge interest, which should be clear, in game theory in the context of machine learning. And from this point now, we will take a more abstract approach on the game theory, but this is really just giving you some context why we can, on an abstract level, learn very important things from game theory, which then really play a role in these machine learning problems. So, as I said, we focus on the critical mathematical abstraction, which are zero-sum games. So these games we saw before really have also the structure that whenever one player wins, the other loses by exactly the same amount. And this is a zero-sum game, as one already knows from the childhood, I guess, where one played, or maybe still even, rock, paper, scissors games, or matching pennies, or other games which are typical zero-sum games. And actually, the theory of games, also in a more scientific way, was mainly developed at the beginning of the 20th century with high interest in economics by John von Neumann, and John von Neumann and Morgenstern, of course, as well. And these first solution concepts that were developed were then, more or less already completed with the idea of a Nash equilibrium by John Nash, where he came up with the crucial equilibrium concept for games, the Nash equilibrium, which says that these equilibria are characterized by no incentives for any of the players to deviate from the current strategies. This is a very static point of view, and it's not clear a priori if you approach these Nash equilibria, if you look at it dynamically, starting from some other parts of your state space, or from other strategies or mixtures of strategies. And the dynamical point of view has then been developed more and more in recent decades. And actually, what one could see is that this question of asymptotic stability in dynamics, it's not always clear that you really converge to these Nash equilibria, but in different models, they can also be conservative or homotone structures. This has made this whole problem of dynamics around Nash equilibria much more interesting, because the Nash equilibrium can't really be the final answer. In particular, if you have these conservative structures, it's not, it is very interesting, of course, to see how these structures behave under perturbations. So they are very sensitive, of course, to perturbations. And in particular, you might have random noise in your games, you might have uncertainties, which is of high interest, of course, also in these machine learning applications, how small noise perturbations affect these games, and especially this game dynamics. And this has led us to considering in more detail now some aspects of stochastic dynamics, which describe the impacts of the noise on the asymptotic outcomes of the game. And the way we describe asymptotic outcomes of games is by characterizing invariant or ergodic measures for the stochastic process, which we will see in the game dynamics. So let me give you a short overview over the contents I want to discuss in the next minutes. So the first part will be mostly, I guess, for most people, a recap of the deterministic case for game theory, but people who are new to this kind of area but have a dynamical systems background, I think, can really nicely go into it with this kind of introduction very quickly. And in this deterministic situation, I will discuss the basics of two-agent models and its equilibria, and then also how the dynamics come into the game as replicator dynamics, in particular in zero-sum games. And in the second part, focus on a model which comprises a stochastic differential equation, and we will present a main result and its proof for this SDE model around the replicator dynamics, which we will then illustrate a little bit with an example and interpret in a summary. So let's start with these two-agent models. So consider some two-player game where one player has N and the other player M, pure strategy at his or her disposal. The game is actually determined by the payoff matrices A and B, which give payoffs for the first player, in the case A, and B in the second player case, for each combination of strategies I and j, which are taken from this number of strategies n and m. At each round, a player chooses a mixed strategy. So player one, we will always say, chooses a mixed strategy X, and second player Y. And mixed strategy means that each possible strategy is attributed a certain probability. So you randomize as a player, and you say with a certain probability I play this one strategy I, and with another probability I play the strategy K. And by that, the state space of possible strategies is given by simplices. Yeah? So for both players, we have simplices. We take the open sets here in this case. This makes the whole analysis a little bit easier later. But of course, the state space as such is really the closure of these simplices, which consist of these probability distributions, which we call mixed strategies. So we have a sense of probability here, but the dynamics we will look at first are completely deterministic. So the stochasticity or the noise that comes into the game is not, by that we don't mean this kind of idea of a mixed strategy, but we will mean really some perturbations in the dynamics later. Another point that is very important is to mention that the utility for each player and each strategy is given exactly by the payoff for player one, always determined by A, multiplied with the strategy that is played by the other player. And for a certain strategy I, this is then exactly the ith entry of this vector. And analogously for the second player and the payoff matrix B. And these utilities, they will of course determine then also our dynamics, and they are the crucial measure of comparing strategies. A strategy profile is a Nash equilibrium, already mentioned. If there are no unilateral profitable deviations, that means there's no incentive to deviate for any of the player. And to check this analytically, one just needs to see that for this kind of combination of strategies P for the first player and Q for the second player, there's no fixed strategy I or J such that the utility of playing this is higher than the expectation you get from this kind of combination. This is exactly expressing no incentives here to deviate. So let's now focus a little bit more on these equilibria in so-called zero-sum games. So what is a zero-sum game? Again, let's say our domain is given by this product of the two simplices. And zero-sum then means that the payoff matrices are anti-symmetric, such that actually the under any kind of strategy combination, the utility the first player gets and the utility the second player gets sum up to zero-sum. We additionally introduce a concept that will be important later for some arguments also in the stochastic case, and that's the idea of an anti-equilibrium P star Q star, which is the Nash equilibrium for the payoff matrices with reversed sign. A way to interpret this is also to say that we could say the payoffs are now costs that shall be minimized, and the equilibrium characterization is then really given by this kind of inequality that we saw before, but now reversed. So now, of course, you don't want that these costs for any fixed strategies are smaller than your equilibrium cost expectation, and that's why you can manifest it in this kind of condition. So there's one difference or one distinction we need to make, and that's between equilibria that are fully supported and ones that are not fully supported. For that, we introduced the idea of a support, and this is just the index set for a particular strategy P, where the weights or the probabilities of the strategies are bigger than 0. And we call a Nash equilibrium interior or fully mixed if it's fully supported. So if all the weights probabilities are bigger than 0 for all indices. And in this case, actually the above inequalities, like here in this kind of equilibrium condition, and this is the anti-equilibrium condition. The equilibrium condition was reversed, as you saw before. In the case of the Nash equilibrium, these inequalities hold as equalities. And by that also any interior Nash equilibrium is also on anti-equilibrium. And this is quite easy to see. The important thing is now the aforementioned distinction between these interior Nash equilibria and potential Nash equilibria which are not fully mixed, but which have a certain support on the boundary, and there will always be a Nash equilibrium with unique maximum support, and the same for the anti-equilibrium. This is an important distinction because we will take some properties of interior Nash equilibrium for understanding the stochastic case, but these situations with the non-interior Nash equilibrium that can also occur quite often, and I think they are not really regarded enough in many contexts, but they have to be regarded, especially if we want to give a full picture. And we want to state the following important lemma, an observation that we made actually on the fly for coming to our stochastic results, which we really needed to take from the deterministic case to give the right categorization and ordering of the problem. And that's the following. So if you have any generic zero-sum game, that means generic in this case among the games, anything of full measure. It's not really important. We could modify this to any zero-sum game with some technical assumptions, but this is how we formulated the lemma. But let's just say any typical zero-sum game with a equilibrium and anti-equilibrium of maximum support has the property that either both of them are interior and then they are the same, and they have fully mixed strategies, and equilibrium and anti-equilibrium are the same. Or if they are just having a maximum support, which is not the full support, then actually the support of the equilibrium, or the union of the supports for each players for the equilibrium, is not a proper subset of the support of the anti-equilibrium in the union for two players, and the other way around. So the two supports are not proper subsets of each other, but they might have, of course, intersections in their supports. But the equilibrium always has some index with a support or some strategy where there is a positive probability in this kind of equilibrium strategy, which is not contained in the support of the anti-equilibrium, and vice versa. So this is important because this gives us some division of the state space into different properties, and this will help us actually to organize the state space then also in terms of the stochastic dynamics. And yeah, as I said, this is a crucial insight for characterizing stochastic dynamics then when we don't have fully mixed equilibria. So let us now come to the dynamics. Of course, it's a very natural assumption. I would say that the agents want to update their mixed strategies in the direction of improving utility. And the natural way to put this into an equation is the so-called replicator equation, which is a key model of evolutionary game theory and online optimization. And it has the following form. So the idea is that if I have a certain mixed strategy X and a utility vector U, then in each component, so in each strategy direction Xi, I want to compare the utility I only get from this strategy with the expected utility under playing this mixed strategy. And if this utility I get from only playing I is actually higher than this expected utility from my currently played mixed strategy, then this shows that I should probably increase the weight on my strategy I. And here in the replicator equation, this is done in a linear way, so proportionally to what kind of probability I already have in Xi. I multiply this this difference of the utilities. And when, of course, this utility is smaller for I than what I get from the mixed strategy, then it means I should probably, I should definitely decrease my probability for playing I, and in that sense, this is exactly incorporated in this equation. So in our case, with the two-player games, the utilities you hopefully remember were given by these entries of this payoff vector, and this kind of equation is now exactly just translated into this two-player setting, and this is exactly the deterministic ODE for the typical replicator dynamics that we have in mind. So let me briefly mention two important characterizations of the deterministic dynamics, deterministic replicator dynamics, which will also be important for the stochastic dynamics, again along this distinction of fully and non-fully mixed equilibria. Firstly, let's assume that for these replicator dynamics, we have it's a zero-sum game, and we have a fully mixed Nash equilibrium, so completely supported everywhere. Then, given any starting point for trajectories x, dy, t, the cross entropy between this equilibrium and any state at this of this trajectory of the game x, dy, t, given as this kind of sum, so this typical entropy formula, is actually a constant of motion. So this means this organizes dynamics in a conservative way, and we actually have constant entropy levels all around our state space. So this is for the interior Nash equilibrium setting. For non-fully mixed Nash equilibria and corresponding anti-equilibria of maximal support on the boundary, we have that there is actually, for the equilibrium case PQ, there's actually a decrease of entropy. And for the anti-equilibrium case, there's an increase of entropy. Yeah, as you might imagine, of course, the non-fully mixed Nash equilibrium will be on the boundary. So for any interior trajectories, I will actually have some will actually make this clearer in a bit, but the tendency and the intuition is, I think, quite clear that these trajectories will rather go to this Nash equilibrium on the boundary, and by that the entropy will decrease from the interior, and the anti-equilibrium case is, of course, exactly the opposite case. So let me elaborate a little bit more on this second part of the lemma. The interior Nash equilibrium case is pretty clearly organized by the constant cross entropy. The non fully mixed equilibrium case, so only with maximum support, is then always accompanied by some set on the boundary, which is associated with these index sets of the maximum support. So this is basically the maximum support part of the boundary. We denote this by delta 1. So this is where the strategies from the complement of our maximum support are all 0, or are all evaluated with probability 0. And then we can actually use this second part of the lemma we just showed to say that in this non-interior case, given any interior starting point, an orbit along our replicator dynamics converges to the boundary of the state space, as I already kind of anticipated. And to be more precise, if there is an equilibrium of maximum support on this delta 1 as a subset of the boundary, then actually the omega limit set of any of these trajectories starting in the interior of our state space will go to the interior of this delta 1, so we'll go to precisely this part of the boundary. I want to illustrate these two distinctions again with an example now. So we have chosen the matching pennies example, which is an easy 2x2 game, one of the easiest zero-sum games you can think of, but it already illustrates quite nicely the distinct behavior. So in the easy case of just 2x2, we have an interior Nash equilibrium, and it sits in the center of our state space. And actually these different entropy levels, they correspond with different periodic orbits around this equilibrium. So already to say it in terms of invariant measures, there are infinitely many invariant measures concentrated on these different orbits. And we have very characteristic conservative dynamics. Now, if we add a certain direction, which is not favorable to one of the players, this can lead then to having a non-interior Nash equilibrium, but one which is on the boundary and supported then on a particular part of the boundary, where different trajectories converge to, but then on this part of the boundary, this was our delta 1, we actually have these different periodic orbits, again as limiting objects, now as exactly the omega limit sets I mentioned in the statement before. And yeah, we see exactly what we said, this convergence to different omega limit sets on this delta 1 part of the boundary. Okay, so this is it from the deterministic side, and now we want to focus on the stochastic model. So this looks as follows. We have a stochastic differential equation, which is like a perturbation, stochastic perturbation of our, as you have seen it already, replicator model from the deterministic side. So we have the deterministic part in these two cases here. And we have this kind of noise, which is a priori looks a little bit yeah, doesn't really look well to comprehend, but we will see in a second that it follows a very clear and nice interpretation. I just wanted to show it to you component-wise because this really is quite recognizable in comparison to the deterministic dynamics. These noise parts here are independent Brownian motions, so these are noise vectors with certain intensities, sigma 1 to sigma n and eta 1 to eta m. And the easier way to look at this, to look at it in this following matrix form. So it's an easy computation that this component-wise form corresponds with this kind of matrix form, where you have in the x and y strategies this this kind of matrix here on the left side, and then you have the just the deterministic part, which is this utility vector, and this utility vector now is perturbed in all directions by white noise, with the idea that there's some normal distribution around these utility vectors, which express some symmetric uncertainty about our utilities there. And I think this is the most natural model you can work with in this context. We can tune the noise to be very small, just small uncertainties around these around these utility vectors, but it's very realistic, of course, that you don't always know exactly what the payoff or the outcome in terms of your utility will be from each round. And this is expressed here and in text just summarized again, that the random fluctuations here are given around the deterministic utility given by these AY and BX vectors. This is a similar kind of model to what Hofbauer and Imhoff did in 2009 for monometrics games, but slightly different. They had a different kind of rationale for deriving such a model. And in particular, they didn't focus so much on these cases with non-interior equilibria. So I think this is quite a nice complementary work on stochastic dynamics in these replicator games. So we will now introduce briefly what is our main tool for understanding the stochastic dynamics and their invariant measures. To understand what happens to observables along trajectories, and this really helps to characterize the whole stochastic dynamics, one looks at the generator here written by calligraphic L of the solution process, the Markov process, which solves the stochastic differential equation. And this generator, in this context also called backward Kolmogorov operator, acts on twice differentiable functions, which are the observables. And actually, yeah, as a generator characterizes the infinitesimal time derivative behavior of observables along trajectories. So in more detail, this LH is actually the same as taking the time limit from above of this object, so of this expected value starting at xy of our observable evaluated at xtyt as the process solving the SDE minus h of xy. So this is really, in a way, this time derivative at 0 from above of h along our trajectory, solving the problem. So this is the sign of this, and this will be the crucial thing for the following. The sign of this really shows us if at a certain point we can observe our can expect our observable to increase or decrease. And if we know that, for example, this observable going to the boundary goes up to infinity and it increases close to the boundary everywhere along these trajectories, then of course there's some technique to derive that then our trajectories will actually go to the boundary and the other way around. And this operator itself actually has the form of a second order differential operator with a first order part where the prefactors are given by the drift from our stochastic differential equation, and the second order part with diffusion matrices, which come from the coefficients of the SDE on the noisy part, which are in our case, yeah, as you hopefully have seen on the slide before, given by these kind of matrices. So we want to work with this operator to determine the sign of this derivative, and this will help us then with some formal arguments to derive where stochastic trajectories are going. So a candidate as an observable, of course, is this entropy function from the deterministic case, which already has quite a lot of properties we know for the drift part, so for the deterministic part, which we can use in the following. So if we have any kind of equilibrium, pi, qi, for now we cannot say if this is fully supported or not. Then we can apply our operator to this observable v. And what we actually get then is the sum of these two parts. So this is the first order part, is the second order part. And you see that the second order part always has a positive sign. So this will determine some diffusion to the outside, or not to the outside, but rather away from the interior, or at least something that's which smears out your dynamics along and around the state space. And the drift part and its sign, of course, in comparison to this part, will determine the overall sign. So this drift part we call L, and we remember that for PIQI being Equilibria, this will be smaller equal than 0. So without the minus here, this was bigger equal than 0. We had that before. But with the minus, it's now smaller equal than 0. And in the interior case, if the Nash equilibrium is interior, then this is actually equal to 0. Because this was exactly then coming from these deviation inequalities, which become equalities in the interior Nash equilibrium case. And in the non-interior case, remember, this is very much related to what we saw in this theorem or lemma about the entropy increase or decrease. In this case, then for only maximal support but not interior, this will be negative. So this should be for non-interior equilibrium of maximal support. This function here will be negative for any point inside our state space. So we will use that in the following to prove this main theorem that has been our work in the last months. So consider this SDE model of stochastic replicator dynamics. Then we can say that any invariant probability measure, so anything that characterizes stochastic mass being distributed in our state space, will actually be supported on the boundary. So trajectories will not stay inside, but will always converge to these invariant measures on the boundary. And in particular, these invariant measures are ergodic, namely they are given by convex combinations of the ergodic Dirac measures sitting on the corners. And we can derive this by distinguishing in more detail the two different cases again. So if the Nash equilibrium is interior, then all these corners are actually attracting with respect to interior. So we have the spreading to the boundary in a uniform way. On the boundary, then there might be, of course, still different dynamics depending on the noise strength, but independent on any kind of noise strength, we have really the spreading of the dynamics to these different corners of the state space, and these invariant measures are supported on these corners. If the Nash equilibrium is non-interior, but there's only a Nash equilibrium with maximal support, then for the large noise case, which is potentially not so interesting, but we still want to mention it, we have the destruction of these kind of finer structures of the drift dynamics, and we will again be spread just completely to the outside, to these corners. But for the small case, which is probably the more interesting case, because we would assume that our perturbations are hopefully not too large around the deterministic model, the only invariant measures which are actually attracting the interior are contained in the subset delta 1 of our boundary, which contains exactly the Nash equilibrium of maximal support. So we have the correspondence with the deterministic dynamics there. But then, of course, once there is an interior Nash equilibrium in this subspace of the boundary, then we will again, as we have from the previous part, see a convergence to these corners of the state space. So summarizing, this theorem really says that our stochastic dynamics of this model only have invariant measures which are supported on these corners of the state space. So there are some combinations of this, and the small noise or any kind of perturbation of this replicator model doesn't really allow, at least in this kind of perturbation scenario, it doesn't allow for any interior measures, not anything which is distributed around these mixed strategies in the interior, but we really will have the effect of players only choosing certain fixed strategies with probabilities 1 or 0 in certain combinations. And I want to, because I did all this preliminary work on the different methods, or on the main method we're using and the different aspects of that, that I want to go briefly into the proof of this theorem. So the first part is easy. If the Nash equilibrium PQ is interior, we can just look at this cross entropy function again and take this as a Lyapunov function. It is easy because this drift part vanishes, as I said. This is what we call L. So if we introduce this h, this function h, as the function which comes out if you apply the generator to this cross entropy function v, then the only part that stays is this noisy part. And this will actually be always positive on the whole state space, in particular uniformly bounded at the boundary of our domain, such that, yeah, our entropy or our generator applied to the entropy in terms of this h is completely uniformly positive, and the entropy itself, this goes to infinity at the boundary, but then this kind of derivative given by h, this is also positive, especially at the boundary. So we will have accumulation of stochastic trajectories to the boundary. And yeah, there are formal ways then to really prove this properly by using some theory, for example, from Benem-Strickler 2019, where they summarize nice methods in this context, which show that the boundary absorbs almost all trajectories, and invariant measures for this case can really only lie on the boundary. And then in particular, if you then apply again the scenario, you will only come to the boundary in the end. But of course, you could have non-interior measures on these boundaries. And for this, we need to look at this second case. So if there's no interior Nash equilibrium, there is, as we said before, there's then at least a non-interior equilibrium with maximal support. And again, we have these sets delta 1 corresponding with the index sets of the maximal support. And also we will now introduce delta 2 as exactly the complementary set, so where the maximal support strategies are all put to 0 on the other side of the boundary. If we now look at the cross entropy function, which is exactly the same as before, but now it's not fully supported. So just to make this clear, I also put the corresponding index set here. Then we see that it's not really a complete Lyapunov function for the whole boundary, because I mean, it's still going to infinity when you go to this delta 2, but for delta 1, it's not going to infinity, since the parts where DLN would actually go to infinity with these parts going to 0, they are not even part of this function, because the PI, QI, they are 0 there. So, sorry, this should be QJ because I chose J here. This is not a complete Lyapunov function, but it will still be helpful for the analysis. And in more detail, we can again divide this H0, which is the generator applied to V0, into these two parts, L0, K0. So the K0 is again this quadratic part coming from the diffusion, the L0 again, this part from the drift. And we now need to see what kind of sign wins. Yeah, we are in the non-interior case, so this L0 will be, apart from some exceptions, be smaller than 0. This K0 will be bigger than 0, and we need to see what kind of sign can win. In addition to this V0, we also now really use this concept of the anti-equilibrium for introducing a function V1, which is exactly the cross entropy associated with the anti-equilibrium. And for this, we can actually say, except for very special cases at certain corner points, which then will compensate with the H0, that actually for all points in our state space, the H1, so the generator applied to V1 will be bigger than 0 because this K1, apart from special points, is always bigger than 0, and the L1 is also bigger equal than 0, exactly as we saw before, coming from this derivative of the entropy for the anti-equilibrium case. So if we now look at two different cases, we can finish this proof. The first case is that our K0 is bigger than the minus L0, so the diffusive part dominates the drift part in our H0 part, which corresponds with the problem at delta 2. So if we have that, so this is kind of the large noise case because this comes from the noise intensities, then we can, very similarly to before, actually combine these two different Lyapunov functions plus potentially another remaining term if there's something on the support, or if there's something on the boundary which is not supported already by the combination of anti-equilibrium and equilibrium. And then with similar arguments as before, I show that the boundary observes almost all trajectories. So this is what I call larger noise case, and we can, as you will see then in the preprint, also give some quantitative characterizations of how large the noise has to be. The second case, now the smaller noise case, is when this K0 is smaller than this minus L0 at some point. Yeah, here first we assume that everywhere the K0 is bigger than the minus L0. Now it's the other way around for 1 point, but if that's the case for 1 point, one can quite easily show that this will be the case for all xy in our delta 2, so in our complement again of the maximal support, where the H0 is then smaller than 0. So this indicates that really we have some repulsion, we have some actually drop of our observable or entropy function when it's close to this part of the boundary. And so this indicates that around this part of the boundary, actually stochastic trajectories will be driven into the interior. At the same time, at delta 1, which we characterize by this Lyapunov function coming from the anti-equilibrium, we always have that H1 is bigger than 0, so we have one attracting, one repelling part, but there will be something in between in this boundary, and we need to characterize the whole stochastic dynamics. So the trick we came up with was to simplify our state space a little bit by actually just categorizing everything into 4 different parts. So the x1 is exactly the sum of for a particular strategy x of the probabilities for this mixed strategy x with the index from our maximal support index I, and the x2 is exactly the one corresponding with the complement, so the sum corresponding with the complement strategies, such that x1 plus x2 equals 1, and then on the y side, y1 and y2 play exactly the same role. So by that, we can actually split the boundary into only 4 branches with 4 kind of corner points, where the A0, 0 is exactly our delta 2, because that's where x1 equals 0, y1 equals 0, or x2 equal 1, y2 equal 1. So that's exactly the complement of our maximal support, where the maximal support strategies are all 0, and the delta 1 is exactly where they are all 1. And this is what we call A11. And A10 and A01 are exactly coming from this 2-player strategy structure, are exactly the 2 different combinations of x1 equal 1, y1 0, and x1 equal 0, y1 equal 1. And with a little sketch, we can now finish the proof. Since we observe that, okay, this H1 bigger than 0 acts like a Lyapunov function here, and it's actually positive, so we have some attraction here. At the H0 smaller than 0, yeah, acts as a measure for this Lyapunov function thing at this corner at the A00, but since it's smaller than 0, we have some repulsion from here, and the 2 corners can now be from two different sides be characterized in a similar way, and we actually can observe that for this small noise case that we assume, the H0 will be smaller zero here in two sides of these corners as well, and such that we can't really have attraction here, but we have always something that repels us from these parts of the boundary as well. So in the end, the only part where really trajectories can accumulate asymptotically is this part, and this is really where then the only attracting from interior attracting invariant measures can lie. And this is really what we need to then iteratively always use the same arguments. So we get this full statement by applying these arguments again and again, because if you imagine, okay, we have, for example, a non-interior equilibrium, and we have a small bit of noise, then we are pushed with all the stochastic trajectories with high probability to this part of the boundary of maximal support. That's where our attracting invariant measures will be. So if on this part of the support there's an interior equilibrium, then we are spread again to the boundary. And then on these boundaries, again, if there's an interior equilibrium, we are again spread to the boundary of this boundary part. Or if it's non-interior, then again we are brought to just this one particular maximal support part of this boundary part of the boundary. So if you have a very high multi-dimensional game, this gives you already a full characterization where you can expect your attracting invariant measures or combinations of invariant measures which are characterized by the corresponding corner points. So this gives you a full characterization of the stochastic dynamics in terms of attracting invariant measures. And yeah, finally, I want to illustrate these results again with the same example from before with the matching pennies. So this is how the two matrices look like for this kind of very easiest zero-sum game. The stochastic differential equation, so they are given by this easy replicator part here in the deterministic drift part, and then this noise part, which comes exactly from the model as we always see it. And it's enough to only look at the x1 and y1 equation, because x2 and y2 are immediately given. Of course, it's 1 minus x1 or 1 minus y1 respectively. So again, as we had before, for the non-noisy part, our invariant measures all lie on these. They are all supported on these periodic orbits around this elliptic equilibrium. Of course, Lebesgue measure for this conservative dynamics is also an invariant measure. So we have all sorts of interior invariant measures. But if we just add a tiny little bit of noise, we actually are completely pressed to the boundary. And what we see is that if we take any typical trajectory, then this will accumulate more and more at the corner. So here we have a completely equal combination of all four corners as our invariant ergodic measure, which is here now expressed in terms of a histogram, actually. So this is a histogram for what we've seen from the one trajectory we will follow. And I just briefly show you a video. So this kind of video shows how the histogram is developing if we collect the points of the stochastic trajectory driven by this stochastic differential equation. And yeah, how points are collected then mainly from a certain point around the corners, which are all attracting for a while, and then the noise pushes them to the other corner, and so on. And we have this kind of combination of the corners as ergodic measure. So I think this illustrates quite nicely exactly what the effect of the noise is here. And now additionally, of course, we want to consider the case with a non-interior equilibrium. So for that, we add a certain strategy for the first player, x3, which is not beneficial at all. And of course, this is an easy cooked up example, but in many more complicated cases, this will appear in a certain complicated way, and this is really just to illustrate nicely what happens. And so we have -2, no matter what the other player plays for this player plays x3. Incorporating this into the dynamics, we need to add another direction now. And yeah, this is just for showing you that one can nicely write down these equations, always with this deterministic and then stochastic part, and simulate them. Actually, we already know what happens analytically, but we can simulate to illustrate. And for the deterministic case, as we saw before, if there's no noise, the trajectory starting here from different initial conditions will all converge to this part of the boundary of the maximum support. So this is where the interior equilibrium lies. So the interior for this part of the boundary. There's no interior for the whole game, but then there's an interior on this maximum support part of the boundary. And for the noisy case, if we have again these different noises into the different directions, we will also see accumulation of points on this side of the boundary as we predicted. But now, of course, since this is an interior equilibrium here on this maximum support part of the boundary, we see exactly what we saw in the sub case before. Trajectories will accumulate here in a certain proportion at these different corners. And now invariant measure will be a combination of these. So I hope this gives you some pictures. All kind of complicated substructures and orderings of this can happen, but this already, I think, gives you a full characterization of the replicator zero-sum case with random fluctuations around utilities. And importantly, you might say now that this is not very surprising. You perturb some conservative structures and you just push to the boundary, but a priori, this was not completely clear to us. I mean, you could also, in the Hofbauer Imhoff case, for example, for a slightly different model, you also can see interior invariant measures. And I think it's important to quantify and make clear that for this particular case, you really only see invariant measures supported on the boundary, and in particular as combinations of these 1-0 strategy combinations. So let's put this into a full summary. We looked at deterministic replicator dynamics with 2 agents, which we have said are also important for machine learning due to these competitive games, which let AI become better at fulfilling certain tasks. And in this case of the deterministic dynamics with 2 agents, the dynamics are organized by a constant of motion when there is an interior Nash equilibrium in this first kind of setting. And otherwise, if there's no interior Nash equilibrium, there's always a maximum support Nash equilibrium on the boundary, and we have convergence of trajectories there. So this already characterizes our replicator dynamics for zero-sum games. And along this distinction, we can now characterize also the stochastic replicator dynamics, which are then important if also in AI or machine learning problems, we have certain small uncertainties, or we actually want to introduce some small noise or uncertainties, in particular to push things out of certain conservative structures. And then we can see that the noise really pushes trajectories towards the boundary for this problem. And the invariant measures, so what that characterize what we can expect from the asymptotic behavior of stochastic trajectories, they are combinations of corner points around some Nash equilibrium. Either it's already interior or it's at least interior for some maximal support part of the boundary. The interpretation that we get from that is that if this is a feasible economic model, then this would tell us that the uncertainty around the utility really disperses the agents to non-mixing strategies. that if there's no real certainty about what the utilities are and what you can expect from these mixed strategies, that you decide to only focus on particular deterministic strategy choices. And yeah, maybe this also can give an interesting insight into some of the economical modeling and the agent-based modeling in general. Yeah, and we hope to pursue with this question also in other terms of stability, and also looking more into the random dynamical system aspect of that. So really trying to understand more what happens to different trajectories, which yeah, then have to be compared in terms of their stability when they converge to the boundary. Do they completely converge in a synchronized way, or do they diverge also in some sort of complicated attractor structure? For now, I thank you very much for your attention and hope that this contributed some interesting aspect to this conference.